we know how the rank of a matrix influences the number of free variables in the collection of solutions for the corresponding homogeneous equation, but not all systems of equations are homogeneous. So what happens to the possible collection of solutions if your system of equations isn't homogeneous? If your system of equations isn't homogeneous, then if we have a system like this that's not homogeneous, so the right-hand side we can write just as B1 all the way down to AM1x1 plus dot 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 up to AMNXN equals Bn. So when we write down the augmented matrix for this, we're going to get all our A's over here, from A11 over to A1n, down to AM1 over to AMN. And then the augmented column is just the B's, B1 through Bn. Right. And there are a few different situations. So first of all, there might not be any solutions. Right? But what would that look like? Well, the way to have no solutions is to have a contradiction somehow, or it's to have 0 on one side of the equation and a number on the other side of the equation, right? To have no solutions, you have to come up with an equation that looks like this. But for that to happen in a reduced row echelon matrix, you'd have to end up with a row that has a 1 here and zeros out here. Right? So this is the only way you can end up with no solutions for your reduced row, for your original system of equations. Unfortunately, there's not really a way to tell just by talking about rank. There's not a way to distinguish this kind of matrix with this sort of special kind of row from other echelon forms that you might see. So just when talking about rank, there's no way to characterize there being no solutions. That's kind of unfortunate. Let's see. So from now on, we'll assume that there is at least one solution, and that means that we don't have any rows that look like this. There isn't a leading 1 in our augmented row. Okay, so from now on, let's say that the rank of our matrix, let's call this whole thing, I'm tired of writing it out, so how I'm gonna name this is A and then vertical bar B. So this is a shorthand for this entire augmented matrix. Okay, so and now we can talk about the rank of this matrix. Right? We can talk about the rank of A vertical bar B, and let's call that rank R. Remember that we had n free variables to begin with, right? x1 up through xn. So the number of variables is just n. Okay, so what could the collection of solutions look like? Well, one nice case is when the rank of the matrix is equal to the number of variables. So in this case, what would your reduced row echelon form look like? Well, you'll end up with some numbers in your augmented column here, so maybe we'll call those C's, right? C1, C2, and so on. And if the rank is equal to the number of columns, that means every column has a leading 1 in it. So that means it's going to look like this. And if you're in reduced row echelon forms and every column has a leading 1 in it, then that means above all of those leading 1s has to be nothing but zeros. And also below those leading 1s have to be nothing but zeros. Okay. Now it's possible that there could be some rows that don't have any leading 1s, but if every column has a leading 1, any row that doesn't have any leading 1 doesn't have anything, and so it's all zeros. Like this. And then finally, what about the in the augmented column for these rows with zeros? Well, if we've already taken care of the case where there are no solutions. So, right, we're assuming that there is at least one solution, but for there to be at least one solution, we have to have zeros here. Otherwise, there would be no solutions. So, in rows, if we do have rows of all zeros, the augmented column has to also have all zeros. So, although there might be m rows in general, only down to Cn could possibly be anything other than 0, right? The rest, anything beyond the nth position in this augmented column has to be 0 just for there to be a solution. But if we read off what this reduced row echelon matrix says about our solutions, it says that x1 is equal to C1, and x2 is equal to C2, and so on, all the way down to xn equal to Cn. So if the rank is equal to the number of columns, then there's no choice in what values your variables have to take on, and that means, as a result, there's a unique solution. All right. Maybe one more case to look at is when the rank is less than the number of columns. So if the rank is less than the number of columns, right, you might have some columns with leading 1s. All right, and we're going to have some augmented stuff. As before, everything below the nth row in the augmented column has to be all zeros. If you have some columns that don't have a leading 1, right, that must be if your rank is less than n, there must be at least one column without a leading 1 in it. But if you have a column without a leading 1, then that variable, call it x of I, that variable has to be free, right? Because it's only rows with leading 1s that sort of lock down what a variable is. So if there's a column with no leading 1, then, or no pivot, if this isn't a pivot column, then that variable is free. And if you have a free variable, then always you get an infinite number of solutions. So in this case, we have an infinite number of solutions. All right. So we sort of knew already that the three possibilities for a linear system of equations are no solutions, unique solution, or an infinite number of solutions. But now we can at least we can distinguish these two, unique solution or infinite number of solutions, based only on the rank. Right? For any system of equations, and remember that here we're talking about a not necessarily homogeneous system. For a not necessarily homogeneous system, the rank determines whether you have a unique solution or an infinite number of solutions. If the rank is n, you have a unique solution, and if it's less than n, then you have an infinite number of solutions.